Thanks a lot for the invitation to this nice conference. So what I want to present is joint work in progress with Arthur César Lebras, Juan Esteban Rodriguez Camargo, Peter Scholze, and to large extent also with Guido Bosco, especially on everything related to the Rham stakes and so on. And so the aim of my talk is to do the following. So I want to explain what the geometrization of Fargues-Scholze or rather its analog introduced by Arthur, what it will predict on the spectral side, and then linked this prediction with Eugen's talks. And so, following the geometrization of Fargues-Scholze, the spectral side is incarnated in divisors on the Fargues-Fontaine curve. And so more precisely, a critical observation in Fargues-Scholze is the following. So we can consider the object div1, denoted with a sub fp to indicate that I consider it as a functor on perfectoid spaces in characteristic P. And when associated to such a perfectoid space, we can consider the degree 1 divisors on the Fargues-Fontaine curve for S. And so these are Cartier divisors, and the degree 1 refers to the fact that they are like locally induced or defined by a width vector of the form Teichmüller lift of something plus p times Teichmüller lift of something else. And the degree 1 comes from the fact that we require that this A1 is a unit and that that thing is topologically nilpotent. And so then it's a basic result in the theory of a Fargues-Fontaine curve that this set of degree 1 divisors is actually equivalent to untilts S sharp over QP of S. Okay, but if we consider divisors on the Fargues-Fontaine curves, then we have to consider these untilts up to an action of Frobenius. And so from here we can see that this V stack div1 over Fp also has the form that it's the diamond of Qp. I mean, the diamond of Qp by definition parametrizes these untilts over Qp, and then we have to mod out the action of Frobenius acting on this V sheaf. And now the important observation is as follows. So if we fix the prime L not equal to P, then QL bar local systems on div1 over Fp bar. So I do the base change of this V sheaf from Fp to Fp bar. Then this identifies with continuous representations with QL bar coefficients of the Weil group of QP. And so here, this base change to FP bar is necessary because after this base change, what we get is not the diamond of QP modulo Frobenius, but the diamond of QP breve, the completion of the maximal unramified extension of QP, modulo the action of some Frobenius. And then the Weil group appears because, okay, the Galois group of QP breve is the inertia subgroup, and then we have to add a discrete subgroup generated by Frobenius, and okay, up to some unraveling that has to be done. This is exactly giving the Weil group. And so this statement is very important for conceptual reasons, because in the Langlands correspondence one wants on the Galois side to see Weil group representations appearing, but they can now be geometrized via local systems on this object diff1 FP. And for example, this object does also not depend on the choice of an algebraic closure of QP, for example. Okay? And so, therefore, in the geometrization, the Galois spectral side gets replaced by the moduli of local systems on diff1 over FP bar. And so, what is going to happen now is that we want to consider the divisors, again of degree 1, on the thick and Fargues-Fontaine curves that have been introduced by Arthur. And so, on a technical note, I will always make implicit assumption that from now on all Gelfand rings and arc stacks and so on that they are quasi-finite dimensional in the sense that Arthur mentioned very quickly. So, but this is needed for technical purposes. Okay. So, I want to recall that these thick and Fargues-Fontaine curves, they were constructed as follows. So, we have to consider some near perfectoid ring over QP. And in this case, the Fargues-Fontaine curve is constructed as a certain push-out of just the classical Fargues-Fontaine curve for the perfectoid ring, which is given by the uniform completion of A. So this object is well defined. And by the fact that this uniform completion will be perfectoid ring in characteristic 0, this Fargues-Fontaine curve will have distinguished divisor, I mean the vanishing locus of Fontaine's theta map. And then at this divisor we can add a Neal thickening provided by this ring G spec of A. One has to be a bit careful where this push-out is taken, but one can take care of it. And we will now study degree 1 divisors on this Fargues-Fontaine curve. And so, first of all, I have to specify what I mean by Cartier divisors. So, this is a notion which makes sense for any Gelfand stack. And I will say divisor or Cartier divisor, but more precisely one should maybe call it a generalized effective Cartier divisor on X. Namely, this is a line bundle, or one can also equivalently say an invertible object, L, in the category of quasi-coherent sheaves on X. So, and this should sit in degree 0. And in fact, one should define these objects to be just a line bundle. But it is equivalent. But it's equipped with a morphism S from L to the structure sheaf on OX. So this is very close to the notion of a Cartier divisor, but there is also an important difference. Namely, we don't demand that this morphism is generated by a regular section. So it can also be 0. And also, it will be very important for this talk also to work in derived, in a derived setup. So it's actually, so in this setup, there's only this notion which is really reasonable. Okay. But what's very convenient is that this datum of such a Cartier divisor is equivalent to a map from X to A1 modulo GM. And this is a map of Gelfand stacks. So here, okay, GM is the Gelfand stack sending some Gelfand ring to its group of units. And A1 is just taking the additive group, and then one has an obvious quotient. And here roughly the A1 is parametrizing the section for the trivial bundle, but then quotienting out GM replaces here the trivial bundle by L. And so now what's missing, we have to define this degree 1 condition. And this is the following. So if we have a nilperfectoid ring, over QP, then we say that a Cartier divisor on the Fargues-Fontaine curve for A is of degree 1 if its base change to the classical Fargues-Fontaine curve is of degree 1. In the classical sense. And then secondly, div1 is the Gelfand stack sending A to the anima or groupoid of degree 1 divisors. D inside the Fargues-Fontaine curve. So here, again, a warning. I write D inside the Fargues-Fontaine curve, but this is only some notation. It's not meant to say that this is a monomorphism.
Can it be more complicated than a groupoid that is, because of the derived notions, can you have a higher homotopy of the automorphism of an object?
Here, the ring A, like the way how we set up a theory, can be any animated ring, and so I don't think that we can get a bound on the homotopy group C of this thing. Okay, and so I want to make a remark. So there is a very strong analogy between diff1 and an object constructed from prismatization, namely the prismatization of ZP parameterizes so-called Cartier-Witt divisors and Witt vectors, and they are roughly of the same form as before. So they are Cartier divisors in the derived sense generated by elements and Witt vectors, which are also of degree 1 in the sense above, roughly. But more precisely, because we only work in a setup where the Frobenius is bijective, the analog should be the perfected prismatization. But then we also, in the Fargues-Fontaine curve, we mod out the Frobenius. So we also mod out the Frobenius on the perfected prismatization here. So to be precise, this is the prismatization constructed by Leary. And so therefore, in this project on analytic prismatization, one can also define the prismatization of QP, again perfected, modulo Frobenius, to be this object diff1. And so in this way one gets, we will see some close connection to cohomology theories and to prismatization. And good. So what I want to do next, I want to introduce a variant of this Gelfand-Stack diff1. And for this I want to recall that Arthur gave the following construction. So whenever we have an arc stack over QP, and I should maybe say that it's quite easy to construct interesting arc stacks over QP, namely arc stacks over QP are just the same as arc stacks over FP living over the diamond of QP. So for example, one can take bun G or diff1 FP as an object inside here and base change it to p-adic QP, and one gets interesting arc stacks over QP. And to any of these, one can associate its de Rham stack, which is then a Gelfand stack. And it's just given by the formula sending some new perfectoid to X evaluated on the uniform completion of A. So this appeared in Arthur's talk. And similarly, if X is a Gelfand stack, then the de Rham stack was by definition the de Rham stack of its associated arc stack. And so now, what I will also be interested in is the de Rham stack of this Gelfand stack diff1. And so unraveling the definition, this is just the functor sending some new perfectoid to the same groupoid over there. So it's degree 1 divisors on the Fargues-Fontaine curve for the uniform completion. And so in other words, one could also write this as the de Rham stack of some arc stack, and this arc stack is given by diff1 over FP, but then base changed to QP. And so this is also the object which in our joint project with Guido we called the Yodo-Kato stack of diff1 FP. And so I want to recall another statement that appeared in Arthur's talk, namely, from the fact that the thickened Fargues-Fontaine curves are defined by such a push-out, one can get a very nice formula for the description of perfect complexes on the thickened Fargues-Fontaine curve, namely if A is near perfectoid, then the perfect complexes on the Fargues-Fontaine curve for A are equivalent to perfect complexes just on the classical Fargues-Fontaine curve, but then one has to also add data at this thickening, so we can consider perfect complexes just on the ring AU, which is just a classical Banach algebra, and then the extra datum is that we have to lift this complex to a perfect complex on A.
So, sorry, just to clarify, so your test category now is just nil perfectoids, or is it defined on all Gelfand rings?
The nil perfectoids over QP, they form a basis for the Gelfand stacks, and so implicitly all the things that I'm writing down are Gelfand stacks, so you can define it.
So you can define the Rham stack this way with this formula. I think last time Arthur Cesarci had to prove this, but I guess what you're saying kind of answers that.
If I remember correctly, you also wrote down this formula only for near perfectoids.
Yes, but I thought it was like something that had to be proven. It was sort of defined as a right adjoint to some forgetful function.
Yes, I mean what's implicit in that statement is that the formula on the right-hand side is indeed a stack, so satisfies the sheaf condition in the Gelfand stacks, and that's some property which needs this property for near perfectoids.
Right, it's a B sheaf on that. Yes.
And so this abstract formula, it implies the following. So let's assume that we have a vector bundle on the Fargues-Fontaine curve for A, and then Arthur already discussed it, and I'm recalling it here. So in Fargues-Schulze, one is very often interested in the global sections of such a vector bundle, say on the Fargues-Fontaine curve, and of course we can map these to global sections just on the classical Fargues-Fontaine curve, but then we can also restrict it to just to the to A. So in other words, we can take E tensored with A over the structure sheaf of the Fargues-Fontaine curve, and this we can restrict further to the uniform completion, and then we have a diagram like this, and this, by this property, will just be a Cartesian diagram. And so in Fargues-Schulze, these objects coming by global sections are usually called BC spaces for Banach-Hermès, and then more precisely we take the A-valued points of this BC space, and on the other side what we would get is the BC space the Rham stack of the BC space for E evaluated on A. And so one sees that actually this cohomology here, okay, one has to prove a bit, but the cohomology that is appearing here, it's really just coming from the classical Fargues-Schulze results. So therefore, this piece is usually well understood, and this was used in Arthur's talk for the following example. So if we take E equal to O, as in Arthur's talk, then we see that BC of O, it sits inside a fiber square. Okay, here, if we restrict E to A, so we just get A. Here we get AU. And here we get BC of O de Rham, but this will just be the de Rham stack of the constant sheaf QP on these stacks, but then one has to calculate that the de Rham stack of such a guy is just this smooth incarnation, and so therefore one sees that that guy here is necessarily isomorphic to this group object QPLA introduced by Arthur. And then secondly, for this talk, it will be important what happens for O1, because classically the diff1 over Fp, it's also the same as BCO1 modulo the action of QP cross, and something similar will happen here. So what do we get for O1? So here, okay, we know that we have to, here I should write A1, and here I should write A1 de Rham, because these will evaluate to the thing below. And so again here, we have these guys. And now the thing on appearing here can be calculated by invoking Fargues-Fontaine. And so what do we get? We get an object that I want to call 1 plus d tilde de Rham. And here, this 1 plus d tilde, it should be defined as the inverse limit over the multiplication by p map on just 1 plus d, where d is the open unit disk. And so why is this object appearing here? Namely, if we consider some nilperfectoid and it's the A-valued points, then what do we get? We would get p-power compatible systems in the uniform completion of A, but this is the same as in the uniform completion, when tilted, and then topological nilpotent elements. So this is that we get here, and this is actually exactly the formula that one gets by Fargues-Fontaine. Okay, so in particular, and this map, so if we have such a compatible system, so here that thing is an element in AU, then we can map it to an element here by taking the logarithm of U. And so this will define an object in A1 de Rham. But now you see that we actually have a natural map from this inverse limit down here, namely if we have now a p-power compatible system of elements where now the Q is an element in A, then we can again just send this element to the logarithm of Q, and then clearly we have a map from this guy to there. So we get a map from here, which means a map from here. And then just because that thing has to be Cartesian, and one checks also that the outer diagram is Cartesian, one sees that this is an isomorphism. And so the geometry of the diff1 and diff1 de Rham can be described by the following theorem. So we want to understand diff1. We have a natural map to diff1 de Rham. This comes with a map to A1 de Rham modulo GM de Rham. And diff1 has a map to A1 modulo GM. And this square is actually Cartesian.
Johannes, sorry, could I just try to understand? So there's 1 plus d tilde. Is this then an example of an affinoid object where the ring of functions is a non-completed filtered colimit?
Yes, this inverse limit is happening in Gelfand stacks. I mean, it's not an affinoid object because it's the open unit disk, but locally, maybe I should. So this is the open unit disk. But locally, you will get an uncompleted ring of functions. And the transition maps, they are all étale. Okay, so when div1 is isomorphic to the BC of O1, when we remove 0 and mod out the action of QP cross LA. So, namely, it is clear that we have an action of BC of O on the BC space for O1. In other words, if we puncture this BC space, then we get an action of the units in QPLA. And in fact, under this isomorphism, this is just the usual action that you would write down. So meaning that here, if you take A in QP cross LA and Q inside 1 plus D tilde, then the action is given by Q to VA. I mean, one has, well, this formula, okay, it may not make immediately sense, but using this formula, passing to rings of functions, and then using some power series expansion, one can make sense out of this. Then, secondly, so because of these maps, one sees that these div1 spaces, they come with some distinguished point. And so this distinguished point or distinguished locus, if we consider it in div1 de Rham, then that's the following. So we take the base change from A1 de Rham modulo GM de Rham to B GM de Rham. And so that thing is just equivalent to QP. So this point, one could also call it the hot state point. In div1 de Rham. More precisely, maybe one should call it the Rham point, so the terminology is not yet fixed. It's just given by QP. But what about this distinguished locus inside div1? So this is what's called the analytic hot state stack of QP. So we take div1 over A1 mod GM and we base change to BGM. So this guy, okay, it of course has a map to G spec of QP, and this is a non-trivial GM dagger gerb, where GM dagger is the kernel of a map from GM to GM de Rham. So it's the overconvergent neighborhood of the unit element in GM. Gerb. And in fact, this hot state stack can also be calculated to be given by the uncompleted cyclotomic extension over QP. So I join all p power roots of unity to QP, and then I mod out the action of the locally analytic version of Galois group ZP cross. And then from the structure of this group, one sees that this is also actually a gerb over QP. And the proof is actually very pleasant. Namely, we are parametrizing Cartier divisors. And so where does this diagram come from? It again comes from the fact that the Fargues-Fontaine curve is defined as such a push-out. So if we have a divisor on the Fargues-Fontaine curve, we can restrict it to G spec of A, and this defines a point in A1 mod GM. And similarly, we can also restrict it to the Fargues-Fontaine curve for AU, and then also restrict it further to a Cartier divisor on AU. So what we are using here is actually that we profit from the fact that the Cartier divisors, that we consider are always derived, and so there's no problem with any pullback. So it's completely functorial. And so in particular, one sees that one gets very easily some derived structure appearing here in this situation. But that's actually a feature. But then, okay, this diagram comes from describing divisors on such a push-out, but then we can in fact describe all the perfect complexes on A and also morphisms between them. And so this immediately implies that this diagram is Cartesian. And similarly, you can also conclude too and then let's move to the statement 3. So here one can either, we have a complete explicit map here, this logarithm map, and we are now modding out some action of a group and then taking a fiber. So one can do an explicit calculation and see that one ends up with a stack equivalent to QP. But one could also observe, so this point, this new point in diff1 de Rham that appears in the description of diff1 de Rham as the de Rham stack of diff1 over fp, this distinguished point is just the graph of a morphism from p-adic qp to diff1. Okay, so there's some unraveling of some identification involved, but okay, one can do this. But then the graph, the de Rham stack of a graph is just the de Rham stack of QP, and the de Rham stack of QP is just QP. Okay, so this implies that statement. And then the fourth statement. So we have this pullback diagram, and now if you replace the bottom row by the maps on BGM to BGM de Rham, that you see that the fiber is just BGM dagger, and then you also see by the base change that the thing that you get over here, which is the analytic hot state locus, is a gerb over QP, G-spec QP. So here we just have to use one. Okay, that's for the gerb property, but then for this description, what can we do? We just use this explicit description of a BCO1 that we have. And then if you do this if you do this fiber product, then you see that you end up with this presentation here. So let me make some remarks. So in this analytic hot state stack, so we can write it as the fiber product of BGM over BGM de Rham with G-spec of QP. And so when I saw this formula for the first time, I was very confused. Namely, it looks so simple, but why can it be some, before I thought that this analytic hot state stack is something interesting, but then one has to realize that this map from G-spec of QP to BGM de Rham is actually very interesting. Namely, okay, one has to first understand what are GM de Rham torsors on QP. And so here one has to use the GM de Rham torsors. The way how the formalism is set up, these are equivalent to pro-état line bundles. on QP. So that's actually, it's not specific to QP, but I only mention it in this case. And so then one can ask, okay, what is the projectile line bundle classified by this torsor? And it classifies the line bundle which is coming from the GR1 of BD Rham, and so this is O hat Tate twist 1, and so the Tate twist appears, and this makes this map interesting. Okay. Then in relation to the BC spaces, one can also make the following observation, namely,
what is a projectile line bundle on QP?
Pardon?
What is a projectile line bundle on QP?
You consider the projectile side of QP, and then it's a line bundle for the structure sheaf O hat on that side. Okay, so what one can observe is that the situation that I'm describing here is not completely parallel to the case of Fargues-Scholze, because, say, looking at this formula, the geometric objects that we are considering are base changed from FP to p-adic QP. And so this yields something new, namely it yields a canonical short exact sequence namely we have now always a distinguished point on the Fargues-Fontaine curve, and so we can take O1, we can evaluate it on AU, so more precisely we take A lower star infinity, and so we canonically can consider this kernel, and this kernel is locally isomorphic to the structure sheaf of the class of the Fargues-Fontaine curve for AU, and so this is interesting because this gives a canonical. Okay, if we consider now global sections of this bundle, then what we can observe is that there actually exists a map to the BC of O1. So actually, here I'm not considering the BC O1 de Rham, but really BC of O1. And so this has a natural map by this presentation to BGM. And so this implies that there exists a canonical line bundle on that thing, which one can maybe use to cook up a canonical Whittaker sheaf with QP coefficients, but on that guy. Okay. So, but what I'm supposed to do is I'm supposed to move to the spectral side, and so I now have to speak about vector bundles on these spaces of degree 1 divisors, and the following statement is basically just a theorem of Berger, namely we have a very explicit presentation of a diff1. And from using this explicit description, one can quite easily see by some Frobenius spreading out technique that the category of vector bundles on diff1 is actually just equivalent to the category of phi gamma modules over the Robber ring. And so then what one can also see is that this is equivalent to Galois equivariant vector bundles for the Galois group QP on the Fargues-Fontaine curve for CP flat. And so this statement is much more difficult than this one. And here one has to use, this is more or less classical result by Berger. One has to use Sen theory and plus a calculation of the locally analytic vectors for ZP cross in the punctured Fargues-Fontaine disk for QP-Saclay. And so this is also commonly denoted by the space Y for QP-Saclay, but we think that it deserves a name on its own, so we call it the punctured Fargues-Fontaine disk. And so if one does this calculation of the locally analytic vectors, then we actually just get the BC of O1 punctured.
Fargues-Fontaine, QP cyclotomic.
This one?
Yes. What is the after Fargues-Fontaine?
QP cyclotomic, yes.
Is it completed?
This one is completed, yes. This is the classical Fargues-Fontaine curve for QP-Saclay, or rather the space Y, which we call the punctured Fargues-Fontaine disk.
And when you say the vectors and functions, or functions on this, or
can you repeat?
when you say local analytic vectors, you mean in analytic functions on this, or in?
Yes. But when you calculate these locally analytic vectors and then you pass to the spectrum again, and then you get a geometric space which agrees with BC01, with a punctured BC of O1. I should also mention that Galpurat has analyzed these vector bundles, and he also proved that they are equivalent to these non-locally analytic version.
Okay, so how's this Frobenius drilling out technique related to what Trina Bertels taught? There's also a spreading out technique using Frobenius. Well, side pointed at it.
I think it's not as deep as Alberto's observation. I mean, he spread it out from some punctual, but yeah, I think so. Yeah, exactly. Yeah, I think so.
So the use of Zen theory makes this argument not work in characteristic P. So if you don't work over QP, but like other ground fields.
The way how the theory is set up, it only makes sense over QP, and so we hope also that one can do something with over ZP, but this will require more work.
What part of the theory actually relies on it working over QP instead of function fields? I'm a bit confused.
Over function fields. Like this theory of a de Rham stack that we do, it just works for QP coefficients. I mean, for the de Rham stack, you have to provide a structure sheaf, and this should be in characteristic 0, because otherwise this analytic de Rham stacks won't work, and so we are a bit forced to this formalism.
So is there a description, you explained a description of vector bundles, is there a description of all quasi-coherent sheaves, or does some of this work for all quasi-coherent sheaves?
At least for perfect complexes, one can make sense out of this, but classically, I think there are only defined notions for vector bundles, and so I stated it in this way. But more precisely, one should have a fully faithful functor from the category of quasi-coherent sheaves on this diff1 to a stack version parametrizing these vector bundles, meaning you take the quotient of a Fargues-Fontaine curve modulo the action of a Galois group. And this functor should also be an equivalence on perfect complexes. Okay. So the next thing to understand is when vector bundles on this diff1 de Rham, and this is actually a reformulation of a p-adic monodromy theorem. And it says the following: so vector bundles on diff1 de Rham are equivalent to the objects that occurred already in Eugen's talk. So these are phi n Gal QP modules over QP unramified. And so here, one important thing to say is that here the Galois action is smooth. So, which is also nice because like with the Rham stack, it converts continuous actions into smooth actions, and so one should expect a smooth action to occur here, and it does. And so this is partially satisfying and partially confusing, I think. Namely, it's satisfying because the objects that you would expect to get on in the geometrization of a smooth local Lagrange correspondence are very much related to the phi and gal QP modules. Namely, more precisely, over QP unramified, what you see are Weil-Deligne representations. QP unramified is not completed. But so it's satisfying that you see the objects occurring in the geometrization of Scholze via motivic methods on the one hand side, but it's also confusing because it's only working over QP unramified. But actually, this change can also be explained geometrically because we consider diff1 over fp, but Scholze in his motivic paper considers diff1 over fp bar. So I think that this should explain this discrepancy here. But then what one can also do is the following. So this is a variant of a result of Haug.
P-adic moduli theorem, the left-hand side is close to or like equivalent to Rham Galois representations.
So there are different. Like I gave a talk, I think 2 times with Pierre in the audience, and he always asked which version of a monodromy theorem. And so there is a version which is the statement that phi partial modules over the Robber rings are equivalent to phi and gal QP module, and it's this statement that I'm referring to here as the p-adic monodromy theorem. Okay. So what's this another theorem? So we want to see the Rham representation, and there's a naive way how one can get them. So we introduce an object diff1 syn, which is a naive version of some yet to be developed analytic syndromification. And so we do something very naive. Namely, we take diff1 and we glue it with diff1 de Rham, and we glue it over an open subset, which is the complement of the hot state point. So we take diff1 modulo the hot state locus. And so just by the diagram above, if we are away from the hot state point, the two things are isomorphic. So we get diff1 de Rham modulo QP without QP. And then what we are doing here is roughly this, okay, if you consider now a vector bundle on this diff1 syn, then okay, it's basically defined on a very large open, so it's only interesting what happens, say, in an overconvergent neighborhood of the hot state point. But then you can observe that on this side, you are roughly speaking about T connections on B plus de Rham, but on this side you speak about honest connections. And then the condition that, first of all, you can observe that for a vector bundle on diff1, it's a condition to extend to a vector bundle on diff1 syn, and this condition is exactly satisfied if over B de Rham the vector bundle becomes trivial. So the connection becomes trivial. And so therefore you see that the condition of being a vector bundle here is exactly the condition of having a de Rham phi gamma module. And so on the spectral side, we are supposed to consider vector bundles on diff1. And so let me make this as a definition. So for any of the spaces diff1, say diff1 de Rham or just be diff1 or symptomic, we can consider log the log sys n, and it should be the Gelfand stack. Sending A to vector bundles on G spec A times diff1 question mark.
Excuse me, did you say where those phi-gamma modules live over?
Over the rubber ring. And so this means that if G check in is equal to GLN, then the G check from Eugen's talk, when one gets when one basically gets Eugen stacks, but there are two differences. First of all, we are using a different test category. And secondly, we are parametrizing rather phi-gamma modules over the rubber ring, but these are equivalent to the Galois equivariant vector bundles on the Fargues-Fontaine curve, also in families. So,
sure, a small thing that you probably mean to say rank n, right?
Ah, yes, yes. Thanks. And so now Eugen, he also wrote down a correspondence linking his Galois equivariant vector bundles with phi n Gal QP modules, and one gets this in this setup as follows. So the inclusions from diff1 into diff1 symptomic, which also contains diff1 de Rham, induce a Hecke correspondence. So, I mean, it's not literally a Hecke correspondence, but it feels a bit like it. From LS diff1 over L diff1 symptomic to LS in diff1 de Rham. And so therefore it seems maybe to be an interesting fact that this Hecke correspondence, or this correspondence that Eugen wrote down, can be realized as a Hecke correspondence, because essentially one is parametrizing modifications of vector bundles here on diff1, respectively diff1 de Rham. So I can And so, from this perspective, one can also remark that we could replace diff1 syn by yet another object. Namely, one could glue two copies of diff1 over the complement of the hot state point. So in other words, here we would be looking at really modifications of vector bundles on diff1. And so then you would get another Hecke correspondence, but this time acting on LSN of diff1. And so an interesting feature of this situation is that one can actually also now move the hot state point and actually get a Hecke correspondence. We get a Hecke stack. Over diff1 de Rham. Namely, the points on diff1 are roughly parameterized by diff1 de Rham, and therefore we can move that point and actually construct a Hecke correspondence which would map LSN diff1 to LSN diff1 times diff1 de Rham. This seems to be an interesting feature. And then finally, let me finish by saying that if we think of a diff1 as a variant of the analytic prismatization of QP, then we also want to get a full theory of analytic prismatization for, say, rigid analytic varieties. And this will be the final definition that I do here. If we have a Gelfand stack, then we can consider its prismatization, which should be another Gelfand stack living over diff1. And rather, it should be the perfect analytic prismatization modulo Frobenius. And it should be the functor ascending some nilperfectoid with a degree 1 Cartier divisor in the associated Fargues-Fontaine curve to X evaluated on D. And so in this way, one gets a theory of analytic prismatization, and it's parallel to the theory of diamonds modulo Frobenius. Namely, if we have any rigid analytic variety, we can consider its diamond, and this will for sure live over the diamond of QP, and then we can also model Frobenius. And so the interesting fact is now that these morphisms, they occur implicitly in the geometrization of Fargues-Scholze because, for example, in the Hecke correspondence, the push forwards along these morphisms relate to étale cohomology. But here in this case, the push forward, that is, the push forward here will calculate pro-étale cohomology and therefore recover the p-adic theory on X as sheaves on diff1. This is where I want to stop.
I was wondering about the div1 sin. So if I were being like totally naive, I would imagine that if you have a Shoto-Kato stack like div1 de Rham, the way you would get a symptomic stack out of it would be that you would have a map to it from a de Rham stack, and then another map to that from to a filtered de Rham stack, and you would take that kind of push out.
Yes, I think one can also do that.
And you get the same answer?
I think on vector bundles and for perfect complex it should be the same.
But it's not the same stack?
I've not checked this in detail, and I think it's a bit subtle where you take the push out in. I mean, if you take the push out really in all Gelfand stacks, it may be a bit out of control.
So could you repeat what the push out was? What was the push out? I mean,
what did I say?
Yeah.
I said you would take a Shoto-Kato stack, it would receive a map from a de Rham stack, and that in turn would map to a filtered de Rham stack. And then you'd take a push out like that. It's kind of, yeah, obvious thing.
So in this picture, so this picture is kind of what you would expect maybe, and in this your picture, the filtration just hides in the div 1. Where is the filtration?
Yes, I think in this picture the filtration it hides in the theory of T connections.
Also conceptually, sorry.
Okay.
Also conceptually speaking, when you write vector bundles on the symptomification, it should be really the phi and Galois modules, right? So somewhere there also, the bottom line, and then via monodromy, via p-adic monodromy, you get to the Rham.
I think this push-out description gives you more directly the phi n filtered model pictures, but this one leads more directly to the Rham Galois representation.
This push-out gives you phi n picture?
Filtered models, yes.
I see.
But this one is, you get the Rham condition more directly.
Okay.
Can you also get a hacker stack of div1 instead of div1 the Rham?
You can, yes, I mean, you can pull it back.
For example.
I mean, that's actually a very good question, because the hacker stack is not the most interesting thing, it's the Sartake kernels. And when the Sartake kernels, we expect them not to be defined over div1 Rham, but only after the base change to div1.
And why do you call this a hacker correspondence?
Because it sits on such a diagram and it is roughly linked to modifications.
Where is hacker?
Are there any further questions?
Yeah. So is there an analog to the algebraic setting, and that if you have like a smooth, proper, rigid space over QP, then you will naturally get a perfect complex over this div1 sin?
Yes. So we expect that if you take proper smooth X, then this map is cohomologically smooth and cohomologically proper. And therefore, the push forward of perfect complex should use the same.
And would you be able to get like all the existing things that we could write down, like for example, Hodge cohomology, Rham cohomology, etc., cohomology outage?
At least if you use also some construction like this naive analytic symptomification. I think that actually this construction you could also do it relative to div1 sin and also get the perfect complexes, including comparison theorems over div1 sin.
Do you expect to get a theory of geometric Sartake in this setting?
I don't know.
Okay. Maybe we can further questions can just be individually, and let's thank